how much extra memory is used, then we'll see collision resolution by progressive overflow. In the topic how much memory is used, we'll see that how and all we'll try to reduce the collisions. So the two techniques or two ways used to reduce the technique is by using a very good hashing function, and the next one is by using an extra memory. So the first one is by using a very good hashing function. Here we are considering the term packing density. It is nothing but the ratio of the number of records to be stored to the number of available spaces. So we get a formula: packet density is equal to R by N, where R is the number of records to be saved and N is the total number of addresses available to save. So packing density actually gives us a measure of the how much amount of space does my file contain. The next technique which is put forward is known as Poisson distribution, which is used for predicting collisions. Okay, here we are able, by using the Poisson distribution, we are able to predict the number of collisions which can occur when we consider the packing density. So here the first question which we need to answer is how many addresses is should have no records assigned to them. So what is P of 0 and what is NP of 0? P of 0 is the probability of addresses having 0 records. So what is NP of 0? NP of 0 is the number of addresses having record 0. Similarly, we go for the next question. How many addresses should have exactly one record assigned? So in this case, we are not having any synonym, and the address will be having one record. So for that, we can find P of 1. So it is the probability of an address having one record, and the number of addresses having one record is N into P of 1. Similarly, we go for the next question. How many addresses should have one record plus one or more synonyms? In the sense, if one address has been in one address, one record has been stored. In addition to that, how many synonyms or how many collisions come to that particular address? So that has been notified with the probability term P of 2, P of 3 and P of 4, where each one record is saved in each, and in addition to that, one more overflow in the case of P of 2 and 2 overflow in the case of P of 3 and 3 overflow in the case of P of 4. So for finding the number of addresses having overflow, we need to use N of P of 2, N of P of 3, N of P of 4. Now the next question which we need to answer is, assuming that only one record can be assigned to each home address, how many overflow records can be expected? So as I've already explained, P of 2 is the probability of having 2 records in an address. So it means that one record is stored in that address and one record is an overflow. Okay, or a collision. Similarly for P of 3 as well. So for finding that, we can have a formula like 1 collision into number of addresses into P of 2 plus 2 into number of addresses into P of 3. In the sense, 2 collision for the number of addresses, then 3 collision for the number of addresses. So this is how the formula goes for finding the number of overflow for which has happened for an address. The next question is, what percentage of records should be overflow records? So we are considering it, we're going for the explanation with an example where we are having 500 records and 104, 107 overflow. So the proportion is 107 divided by 500, that is 21.4%. So it means that 21% of records is not stored in the home address. Instead, it is stored in some other addresses. We need to see where it is stored. So this is another table which explains you, if I'm having a packing density 10 and means 10 records to be saved, and the synonym is 4.8 or it is 5%. What does it mean? The time taken to access each record in this case is 5%. Okay, and consider that I'm having 100 packing density and I'm having a synonym percent of 36.8. In the sense, I'm having 37% of collision rate with the home addresses. Okay. Next topic is collision resolution by progressive overflow. For these collision, I need to have a handling technique. So that is what we are going to see in this topic. So the technique which is introduced here is known as progressive overflow or linear probing. Here it is a collision resolution technique which has been implemented to overcome your collision. So the first thing we need to know is how does it work. Whenever we find a home address based upon a hashing function, I directly enter that into the home address. Now second time you end up with the same home address. What do you do? We search for the empty address which is available down the addresses. Once you come across an empty address, you put that key inside that. Similarly, we keep filling it. Okay, we'll come to a situation that some of the empty spaces are there available above, and the below empty spaces of your memory is already filled. So now in progressive overflow, what do we do means we include a wraparound function, so that now the pointer can move to the beginning of the addresses and fill up the empty spaces and keep moving around, so that the empty spaces are being used effectively. So this is the technique which is implemented in progressive overflow or linear probing. So we'll see that with the help of an example. So here you can see this is the set of memory which is available for usage, and you see an work wraparound which is used for moving to the top of the addresses which is available, so that you can fill up the space. So now we consider with the Adam. If Adam is a key, the home address is 20, so you go straight away, we fill it in the 20. Bats, the home address is 21, you fill it up here. Next is coal with 21. In 21, coal cannot be done because it is already filled. So what do? This space is empty. We fill it up in 22. And Dean is the home address calculated is 22. We come here, it is already filled by coal. So what do? We find that 23 is available. So we fill Dean here. The next is Evans in 20. Now where you go for 20, it is filled. Again we go for 21, it is filled. We go for 22, it is filled. Again 23 filled. 24, it is free. So what do? We put Evans in 24. So this is how your linear probing works. So similar case, consider that it is here and it is available, we fill it up here. Now once and again an entry comes and you comes to know that it is not available. What do? We go to the beginning of the address and we search for an empty one. If an empty one is found, we fill it up. Okay, this is how the linear probing or progressive overflow works. So this is what you see in the table as well. 20 is the actual address of Adam, and that is where it has been filled. Bat's actual address 21, there it is where it will be filled. Call is 21, but 21 is already occupied, so it is filled in 22. 22 is the actual address, but now it is filled in 23 because it is already been filled. 20 is the actual address, the addresses were not available, so it was filled in 24. So this is how the linear probing or progressive overflow work. The search length we'll see by seeing the explanation in the next slide. So here, that is how the linear probing works. So you can tell that by using this linear probing technique, you can tell that because of collision, our keys are saved far from the home address, forming a cluster of records. The process of saving your key far from the home address is known as cluster of records, forming cluster of records. Okay, so now we go for the next term known as search length, where search length refers to the number of accesses required to retrieve a record from the secondary memory. So how many accesses do I need to retrieve a data from the memory? That is known as search length. So we usually use the term average search length, which is nothing but the average number of times required to access the disk to retrieve the record. So the formula comes like this: average search length is equal to total search length divided by total number of records. So we can do the calculation here with the previous values given 1, 1, 2, 2, 5. So why is it? We will just understand why 1, 1, 2, 2, 5. 1, the actual address was 20, so we'll retrieve it by 1 disk access. Actual was 21, so again the search length is 1 by 1 disk access. Again it was 21, but it was in 22, so the search length again becomes 2. It was 22, now I will go for 23, so again 2. It was 20. Now again I keep searching till 24, so the search length becomes 5. So this is how the search length is being calculated. Now we'll go for the average search length formula. 1 plus 1 plus 2 plus 2 plus 5 divided by 5, that is 22, as you see in the previous diagram itself. Okay, this is the search length being added, and this is the value we get. Okay, so we need to find some technique so that we can improve this. We can either improve this by including more address space or more memory. Thank you.